Welcome to the 13th lecture of metal forming.
The next case is slab method or sliding or low friction condition. That means between the die and the workpiece. So this is two dies and in between I have a workpiece. So when I reduce the height of the workpiece or during the upsetting process, there will be some lateral expansion or the outward expansion or outward flow of material. Okay, then only the diameter can increase. So during this outward expansion, what happened? There will be a relative movement in this area. Okay, there will be a relative movement. So this relative movement, actually, this is my bottom region of the upper die, and this is actually the workpiece, top surface of the workpiece. Okay, so when the workpiece starts to move like this in the outward direction, okay, but in the outward direction, the die is stationary. Die only can move in the up and down direction. Okay, but the workpiece is actually moving, or material is actually moving in the outward direction. The die is stationary. So what happened? There will be a relative movement between the die and the workpiece. A relative movement. Okay, this relative motion actually, or the sliding motion between this die and the workpiece create a friction. So there will be a friction force. So for example, here this is a one object. This is a stationary surface. Okay, example, a force F is applied. A friction coefficient between the body and the surface is mu. Okay, or this we can say N. N. That is a normal force acting from the body to the surface. What is the friction force? F is equal to
mu n.
F is equal to mu N. You may know this. Okay, F is equal to mu N. The friction force is equal to coefficient of friction into normal force. Okay. Similarly, here also a frictional force develops. So what is the direction of frictional force? The material moving in this direction. Material moving in this direction. Okay. So actually, this one. I take this figure. So this is my the material actually moving in this direction. Okay. So when we take this element, what is the direction of friction force? This will be the direction of friction force at the interface. In the opposite direction of movement, the friction force is actually in the opposite direction of movement. So here, if you take this element, this is that element, the yellow color element. Okay, in that element, there will be a friction force. What is the friction force value? F is equal to mu n. Mu n. Here, in the die, I am applying a force sigma y. That is the vertical compressive force or compressive stress sigma y. Okay. Then what is the value of friction force? Mu instead of y, instead of n, we can supply mu sigma y. Actually, this is frictional force. It's not frictional force, frictional stress. We can say frictional stress. Frictional stress. If it is a friction force, this is equal to mu, and here I am applying a force. What sigma y? Fy. Fy is the force. Then the normal force will be Fy. So mu Fy will be the frictional force. Here in this is frictional stress mu into sigma y. Instead of force, here vertical direction we apply stress sigma y. Okay, so there will be a friction mu sigma y, friction force. Any doubt in this? So this is a very low friction condition. A friction force will be developed in the interface region between the die and the workpiece, and its value equal to mu into sigma y. This is not friction force, friction stress, mu into sigma y. That is opposite in this direction. This is actually the movement direction. The material from this point material flow outward in this direction. So the friction force will be in this direction. So that is why this direction, these two directions. Okay, mu sigma y. Okay, so there is a friction. Second, the vertical force. For the compression, we should apply some amount of stress, that is equal to sigma y. That is, if you take the element, same force is acting sigma y. This is sigma y. Okay. Then, when we apply a compressive force, what happened? The material actually flow in this outward direction. So, for the outward direction movement of the material, some amount of stress is required. That stress is equal to, or the horizontal stress is equal to, on this element. If you take the element, on this element, sigma x is the horizontal stress in the one side of the element. On the other side, what is the stress is different. Sigma x plus d sigma x. Okay. So, with respect to the direction, in the horizontal direction, the stress will be varied. One direction it is acting sigma x. In the second direction, it is sigma x plus d sigma x is acting in the opposite direction. Okay. So, this is the three different stresses acting on the element. If you take a small element from the workpiece, these are the three stresses are acting. First one is the vertical force sigma y. Second one is the horizontal stress, that is sigma x plus d sigma x and sigma x. The third one is mu into sigma y, that is the stress corresponding to frictional force. Any doubt in this? Okay. So here we take, this is a plane strain condition. This is very important. We analyze this slab method. This is called slab method or sliding or low friction condition. Here we consider this problem as a plane strain problem. Plane strain problem. What is a plane strain problem? Plane strain problem. The plane strain problem is nothing but, here it has a particular width in this direction. The workpiece has a width in this direction. Okay. When we deform the workpiece by compressive force, the height, this height is reduced from S0 to S1. There is a reduction in height. Corresponding to the reduction in height, the diameter from D0 to D1, or the width, that is, or length, we can say length, diameter or length is increased from D0 to D1. But in this direction, we can see a width also. There is no change in width. We assume that the width is constant. That is W0 equal to W1. After forging and before forging, the width is considered same. There is no change in the width. Okay, that is called plane strain condition. So this is actually a rectangular workpiece. In case of rectangular workpiece, we consider as a plane strain condition. That means during the deformation or during the forging operation, the height is reduced, the length is increased, but there is no change in the width direction. So only two change in the dimension, height and length, okay, of the workpiece. The width is maintained as constant, or actually that is an assumption. There is actually the negligible increase in the width also, but we can consider this as a constant. So width is maintained as constant. That is why this problem is called plane strain problem. So we analyze this problem as a plane strain problem. Okay, but there is a stress in that direction. Sigma x, sigma z. Stress in that direction is a direction, but in the z direction, strain is 0. There is no strain in the z direction or in the width direction. Width is maintained as constant. Okay, that is the one of the assumptions used in the slab method of analysis. So in this direction, the width of the workpiece is not varying. W0 equal to W1. There is no change in the width, but there is a reduction in height. Height is reduced. Height is reduced to lower value. The length, that is initially this one is the length. The length will increase after the forging. Okay. So here for the analysis, I am taking an element. So this is my element used for analysis. That is at a, that it has a thickness of, actually this has a thickness of dx. Okay, the element has a thickness of dx. So its thickness is dx. Okay, and this element is located at a distance x distance from the center. X distance from the center. And this total length of this workpiece is 2a. Here A is the distance from the center to the periphery, okay, surface. A. 2A is the total length. So I take an element here. Already I explained the different types of stresses are acting on this element. So this is the element which is shown here, the corresponding element, this one. Okay, it has a dx thickness, sigma y, which is acting in vertical direction, compressive force. For the deformation, we need to apply compressive force. Then mu sigma y is the frictional stress corresponding to friction. What is the corresponding force? What is the corresponding force? Frictional stress is equal to mu into sigma y. What is the corresponding force? Force by area equal to stress. The force is equal to stress into area. Okay, so the frictional stress is equal to mu into sigma y. Then where this stress is acting, this is the direction of frictional stress is acting in this direction, right? This is the interface region where the friction is acting, frictional stress is acting. Okay, that means this is the area where frictional stress is acting. This is the area, this surface. This surface is the area where the stress is acting. So we can take this, we can assume the width is equal to, this width is equal to 1 unit. For the simplification of the analysis, we can take this width is equal to 1 unit. Then what is the area of the shaded region? What is this area? Area equal to dx into 1. Dx into 1, right? Dx into 1. So what is the corresponding force? So here the stress is acting mu sigma y, the stress corresponding to friction. Mu sigma y is acting. So what is the corresponding force? Mu sigma y into area. Area is equal to dx into 1. So this is the frictional force. Similarly, in the bottom region also. In the bottom region also, same force is acting. Okay, so we convert the stress into force, frictional stress into force. So this is actually shown here, mu sigma y. See this, mu sigma y into dx. Mu sigma y into dx into 1. Actually, there is a 1. The dx into 1 is the area of that surface. But here we take the this width is equal to 1 unit. So we can say mu sigma y into dx. Same force is acting in the bottom side also. Okay. Then in this element, in the previous figure, already the sigma x is acting. Sigma x. Corresponding force is equal to, what is the corresponding force? Sigma x is acting here. Force is equal to, we have a surface like this, force into this area. അല്ലെങ്കിൽ ഈ area, this area. What is that area? Area equal to, this is the height, this is equal to 1. So h into 1. So corresponding force is equal to, already sigma x is a force, stress into area equal to h into 1. So sigma x into h into 1 is the corresponding force. That is actually shown here. Sigma x into h. Similarly, in this side, this is sigma x into d sigma x. We can write sigma x into d sigma x into h into 1. We convert into force. And here also we can convert into force, that is equal to sigma y into what is the area, that is equal to dx into 1. Actually this is can be also converted into force, sigma y into dx into 1. So we convert all the force stress values into force values. Okay, next I am going to resolve all the horizontal forces, or balance the horizontal forces, not resolve, balance the horizontal forces. This element will be in equilibrium. Okay, that means all the horizontal forces will be in equilibrium. So here I am taking the direction. And next I am going to balance this. Okay, so here I am taking to the left side, we take positive. Okay, to the left side I am taking positive value, to the right I am taking negative value. So I am going to balance the forces in the horizontal direction. So to the left we can see this force is acting. So H into sigma x plus d sigma x. Okay. Then towards left this force is acting. Mu into plus mu into sigma y into dx. Similarly in the bottom side, this is actually in the interface between the top die and workpiece. Similarly between the bottom die and workpiece also the same force is acting. So we can write plus mu into sigma y into dx between the workpiece and the bottom die. Then any other horizontal force, this one horizontal force, but this is in the opposite direction. So we can give minus h into sigma x equal to 0. We balance all the forces in the horizontal direction. So that is this equation. This is equation equal to 0. Okay, any doubt in this? So first we convert all the forces, all the stress values into force by multiplying with the area. Then we balance all the horizontal forces. Any doubt? Okay. So next is simplification. So here I simplify the equation like this, and again I simplify the same equation. Just rearrange the terms. We got the equation number 12. So here in this equation, we have two unknowns. What are the two unknowns? First unknown is sigma y. Sigma y. I don't know the vertical force which I want to supply. Sigma y on the member, on the workpiece. The second unknown is sigma x. Corresponding to sigma y, some amount of sigma x will be developed. I don't know that value also. So there are two unknowns, sigma x and sigma y. But I have only one equation. Only one equation. Two unknown and one equation. We cannot solve that equation. And we cannot calculate our unknown value, sigma x and sigma y. So how can we calculate this sigma x and sigma y? Anyone? What is the solution? Here I have only one equation and two unknowns. So how can we calculate two unknowns? By means of a second equation. I am introducing a second equation with the same variables, sigma x and sigma y. Then I have two unknowns, two equations. Then I can solve sigma x and sigma y. Okay. So how we got the second equation? The second equation can be developed from the yield criteria. We already studied two yield criteria, Tesca criteria and von Mises criteria. From the yield criteria, the second equation is developed, and the second equation is this one. Sigma x minus sigma y is equal to 2 by root 3 into sigma f. That is equal to sigma dash f. So here I am applying distortion or von Mises energy criteria. Okay, so we already studied this criteria in the first lectures. That is this one. This is the von Mises criteria, and this is actually a triaxial stress system. The equation is only for triaxial stress system. But here in this problem, we consider the problem is a plane strain condition problem. In the plane strain condition problem, we can simplify this equation like this. I am not going to explain this is just for a reference. We can simplify the von Mises criteria like this. Sigma 1 minus sigma 2 is equal to sigma 1 minus sigma 2 is equal to 2 sigma f. That is flow stress. Here we consider strain hardening. That is why instead of sigma y, I am giving sigma f by root 3. So this is the simplified von Mises criteria for a plane strain condition. So sigma x minus sigma y equal to 2 by root 3 of sigma f. Sigma f is the flow stress of the material, that is the amount of stress required for the deformation of the material for a particular strain. That is equal to 2 by root 3 sigma f can be written as sigma dash f. So in a plane strain condition, sigma dash f amount of stress is required for the deformation. Sigma dash f. That is a flow stress corresponding to plane strain condition. This sigma F is the flow stress corresponding to uniaxial tension. Uniaxial tension. This is sigma F corresponding to epsilon 1. Uniaxial tension. But in case of plane strain, this is the amount of stress. Sigma dash F is the amount of stress required for the deformation. Sigma dash F. So we got second equation. This is the second equation. This one is the first equation. This one is the first equation. By considering these two equations, we can solve and we can calculate the sigma y and sigma x. So here in this equation, how we calculate sigma x and sigma y? Just integrate this, differentiate this equation. Differentiate this equation. We got this one. All other terms are constant. So we got this one. So apply this equation number 40 on equation number 12. Here in this equation. This is equation number 12. Substitute here. And after solving, we got, after solving substitution, this we got this equation, then integration. This is not compulsory for studying. Actually, this is just an explanation. Okay. So this is after differentiation, we supplied in the previous equation and we got this equation. This is the differential form. By integration, we got this equation. In this integration, we have a constant c. So this is the final equation with the c value. To find the constant c, we apply the boundary condition. Boundary condition is that this is the workpiece, this is the distance a. When this is my element at a distance x, when x equal to a, at that time, what is the flow stress corresponding sigma x? When x equal to a, at the surface, the sigma x value will be 0. Sigma x value, horizontal stress will be 0. So we apply these boundary conditions here to find the c value, and we calculate the c value here. Then supply this c value here in this equation. We supply this c value in this equation, equation number 60, and we got the equation for sigma y. This is the final equation. How much amount of sigma y has to supply here? How much amount of sigma y has to supply for the deformation? Sigma y equal to sigma dash f, that is the flow stress of the material in plane strain condition. Here our problem is a plane strain problem. Okay, so flow stress of the material in plane strain condition, that is sigma dash f, that is equal to 2 by root 3 of sigma dash f is equal to 2 by root 3 of sigma f. That is the flow stress in the uniaxial tension test. Flow stress in the uniaxial tension stress. Okay, so the flow stress of the material, the pressure or sigma y required for the deformation, that was the design question. So sigma y equal to sigma dash f, the flow stress of the material in the plane strain condition, into e raised to exponential e raised to 2 mu by h into a minus x. This is the formula for calculating sigma y. Okay, this is the formula for calculating sigma y, amount of vertical stress required for the deformation. And here in this, we can see the x value. The x is actually varying. At the center, x is equal to 0. Then x is increasing from 0 to, at this point, x is equal to a. Sorry, at this point. At this point, x equal to a. That is, x is vary from 0 to a. So here we have an x value. That means this is not a constant value. Sigma y is not a constant value. With respect to x, it is varying. It is varying. Okay. So based on this sigma y equation, this variation of sigma y value. Okay. So this sigma y is not constant here. The stress acting on the element actually is not constant. At the center region, there is a particular sigma y where x equal to 0 value. But at this region, some amount of sigma y value is required for deformation where x equal to a. In the center region, here in the center region, some amount of sigma value is required where x equal to a by 2. So with respect to x value variation, the sigma y value, the amount of vertical stress required for the deformation also will vary. That means there is a distribution of sigma y value along this direction, So we can plot that distribution. And this distribution plot is this one. This is the plot of that distribution, sigma y value distribution. Okay. At the center region, we can see at the center region the x is, this is the variation of x. At the center region the x value will be 0. At this surface of the workpiece, x value will be, x is increased from 0 to a. So at the surface x is equal to a. Similarly in the opposite direction also, here x is equal to a. Okay. So here in this equation, both equations are same. This equation and this are same. In this equation, we can supply different values of x. X equal to 0, x is equal to a, x is equal to a, x is equal to a by 2, x is equal to a by 4. So different values we can supply. By supplying different values, we got different values of sigma y, and this variation of sigma y value is shown here. And this sigma y value is actually a exponential curve. What is the reason for that? Here we can see e raised to exponential raised to a minus x. So any variation in x value, correspondingly there will be a sigma y value variation will be a exponential variation. Okay. So here this is the sigma y, maximum sigma y value. This is the minimum sigma y value. Minimum sigma y. This is also minimum sigma y value. Here we can see when x equal to a, from the equation it is clear. When in this equation, when x equal to a, what happened? When this x equal to a, then a minus a equal to 0. E raised to 0. What is the value of e raised to 0?
1.
E raised to 0 is equal to 1. So this term equal to, when x equal to a, this term is equal to 1. That means sigma y equal to sigma f dash. So in this area where x equal to a, or in this area where x equal to a, sigma y equal to sigma f dash. That is actually shown here. See this. In this area and this area, this is equal to sigma dash. This is actually sigma dash f. Okay, sigma dash f. Okay. But in the center region where x equal to 0. X equal to 0. So we got this equation, 2 mu by h into a. So this is the maximum value when x equal to 0, because this is minus x. So any x value equal to 0 means this is the maximum value. Correspondingly, we got the center region when x equal to 0, we got this equation, sigma y equal to sigma dash of exponential 2 raised to mu a by h. But at these 2 points are the minimum value where sigma dash of is active. So this is called friction hill. This variation of the pressure or vertical force or vertical stress in the material during forging. So this is the material. So in this material, maximum stress is experienced in the center region and minimum stress is experienced in the surface region. And there will be a variation like this. A hill, exponential curve we can see here. Exponential curve. This is not a straight line. It is an exponential curve. That variation is called friction hill. This is called friction hill. Okay. So if there is no friction, consider a case where here there is no friction. Then what is the value of mu? What is the value of mu? If there is no friction here, then mu value will be 0. In the previous equation we can see. If the mu value equal to 0, what is the value of sigma y? What is the value of sigma y? E raised to 0 is equal to 1. This term will be 1. Sigma dash f. Then what will be the friction hill? What is the friction hill? What is the variation of friction?
Constant.
It will be constant. It will be like this. And this value will be sigma dash f. sigma dash. There is no friction variation between the throughout the surface of the material. The amount of stress required is equal to the flow stress of the material. But if there is a friction, then what happens? The amount of stress required is increasing exponentially from the surface to the center region, and the maximum is at the center. Okay, so study this formula. Based on this formula, we can draw this friction here, the variation of the friction through the surface of the or through the material surface. Any doubt in this? So this is an exponential increase because any variation in mu actually exponential e raised to mu. Any variation in mu is an exponential increase. Similarly, any variation in A by S ratio, here we can see A by S ratio. In the previous equation also, we can if x is equal to 0, we can see A by S ratio. So this A by S ratio also actually, with the variation of A by S ratio, the amount of stress required is increasing exponentially. E raised to A by H. Any doubt? Any doubt in this? So try to understand this derivation, and from this derivation we develop this amount of stress variation here, and using this we draw a friction hill. Okay. Okay. Friction hill. Any doubt? Actually, the derivation is simple. This is actually the core of this derivation, the balancing of horizontal forces. If we know this value, then we can create this one. Actually, the derivation may not ask in the final exam, but try to understand this. This is the initial first step. Then after the then we apply the yield criteria here. Then we have two equations. We calculate the unknown by means of this integration, and finally we got this equation, the amount of stress required in the vertical direction, sigma y. And by supplying the sigma y value in this previous equation, we can calculate sigma x. So the sigma x value is not an important factor. The sigma y x is equal to sigma y minus sigma dash f. That is also we can calculate, but this one is important. The sigma y, the variation also important, that is friction hill. Okay. So this is the variation. At the tip, this is the maximum region where maximum stress is acting, at the center region. So this is the dipressure distribution. At the tip, it is maximum, and in the surface regions of the material, it is minimum. And the minimum value equal to sigma dash f. And here sigma dash f is the flow stress of the material. Actually, for any material, even if you take the very soft material, some amount of stress is required for the deformation. Okay, if it is a plane strain, that means there is no change in the width direction, we can consider as a plane strain problem. So that is equal to 2 by root 3 of sigma f. Okay, that is the flow stress of the material, that is equal to sigma dash f. This is sigma dash f. Okay, flow stress of the material. And this diagram is actually similar to this one is similar to the previous one, but here we convert into a dimensional step. That means this way here we consider that the variation is actually not sigma y variation, sigma y by sigma dash f variation. So we divide all the sigma y value with the sigma dash f. So when we divide with the sigma dash f, at this point this will be equal to 1. It will change us to 1 because we divide at this point we divide sigma dash f. At this point sigma y is equal to sigma dash f. So at this point we divide sigma dash f with the sigma dash f. So it will be 1. So this is the similar diagram with the by dividing. We convert the diagram into a dimensional step. The vertical ordinate is converted to dimensional step. So here we got 1. Here it is 0. Here it is maximum value. Okay. So same diagram, friction hill. So this is the 3D view of the friction hill. This at the surface in these regions we have minimum stress required for the deformation, that is the flow stress of the material in plane strain condition, and the center region is the maximum pressure required or maximum stress required, vertical stress required for the deformation. And this is actually the top view during the deformation. When we deform a rectangular workpiece, this is actually the top view. Okay, here in this we can see the deformation in this direction is comparatively low than that of the deformation in this direction. Okay, so because this area offer least resistance against the deformation or the material flow compared to this area. That is why this top view will be like this. So the last topic, that is the forging force. So we got a distribution. After the derivation, we got a distribution. So what is, for example, after I apply a particular value for mu and A by S, here I am got, for example, 1. Here I got 3 megapascal. Here I got 5 megapascal. This is 2. This is 1. Okay, so this is the variation of stress, for example. So for the deformation in this region, I need to apply 5 sigma y. In this region, I need to apply 1 sigma y. Here in this region, I need to apply 2 sigma y. Sorry, 2 megapascal value. Okay, for the deformation. Here 2, here 1 megapascal. So this is not constant. The stress required is not constant. So I don't know how much amount of stress is applied. Is it 5 megapascal? It is not 5 megapascal. The 5 megapascal is the stress required for the deformation of the center region only. But in the remaining region, the stress requirement is less than 5 megapascal. So I want to calculate a constant sigma y value. Constant sigma y value. Actually, the sigma y is varying for the deformation. So next step is to calculate this constant sigma y value. That is a forging load calculation. So forging force calculation. We know pressure is equal to force by area. Force by area. Here in this case, so force is equal to pressure into area. Okay. Average pressure. Average forces we are calculating because the stress is actually varying. Pressure or stress. Sigma y also we can say pressure. So pressure or sigma y value is actually varying. At the surface it is minimum, center it is maximum. So we can take the average pressure. Okay. So the average pressure is, that is actually corresponding to this area, the frictional hill area. Same area can be plotted with a constant sigma y or constant pressure. So this area, this hatched red hatched area and this green hatched area will be same. That is the amount of total energy requirement will be same. So corresponding pressure is this P bar. Corresponding pressure or corresponding sigma y will be sigma y bar. Okay, so that's P bar into area. That is the force required for deformation. How much amount of force has to supply by this die for the deformation? That is equal to P bar into A. Okay, so what is the area here? In this area will be equal to, here we can see area where here we apply the sigma y or pressure. So this will be the area. This will be the area. So what is this area? This is equal to 2A. We know this is equal to 2A. This is equal to 1. We take unit width. Okay, so the area will be equal to P bar into, here in this we consider width also for calculation, W. From this onwards we consider width. So that is equal to P bar into 2A into W. So that is this formula. P bar is equal P bar into 2AW. Okay. What is P bar? I don't know the average pressure. To calculate the average pressure, we need to do integration. By integration, we can calculate the average pressure. So this is the distribution. This is the distribution of the sigma y value. Sigma y value distribution. Friction hill. Okay, friction hill. I take a small area here, where the stress is equal to sigma y. Sigma y. And so for the calculation of the total stress, we can do integration. So we can do integration between 0 to a, 0 to a, okay, sigma y by, here we calculate the pressure, so stress by area or length. Here a is the variations of sigma y by a into dx. The variable is dx. So this is the average pressure. Okay, so this is the sigma y value is actually varying. So we calculate the average pressure by integration. In this sigma y value, this sigma y is substituted from the previous derivation. This sigma y is substituted, equation number 19. Okay, equation number 19 is substituted here instead of sigma y. So we got this one, this equation. In this equation, we have a term exponential e raised to 2 mu by h into a minus x into dx. Okay, so we can simplify that exponential term. What is the expansion of e raised to x? Exponential raised to x, 1 plus x, x raised x square by 2 factorial plus x cube by 3 factorial. So if the x value is very small, we can neglect this term because already x is very small, then x square x cube will be further small. Okay, so we can say e raised to x is equal to 1 plus x. Okay, so here in this equation, exponential e raised to 2 mu by h into a minus x into dx can be assumed here e raised to x can be assumed 1 plus x. Here e raised to x term is this one, e raised to x. So we can assume 1 plus, instead of x we can write this one. So 2 mu by h into a minus x into dx. Okay, so we actually approximate this one. So we got this one, this equation. After approximation, we convert the exponential term into 1 plus x. Okay, we got this equation. Then after simplification, I am not going to explain all the steps. After simplification, we got average pressure. Sigma dash f into 1 plus mu a by h. That is the average pressure required for the deformation of the workpiece. Okay, so actually the pressure or sigma y is varying, but we supply average pressure here. Average pressure P bar. Okay, this is the equation for average pressure. This is very important equation. The average pressure required for the deformation. Okay, actually the pressure is varying, sigma y is varying, but using this derivation we calculate the average pressure. So this much amount of pressure has to supply using a die. P bar is the amount of pressure has to supply using a die, or amount of stress. Stress and pressure is actually the force by area. Okay, this much amount of pressure or stress has to supply using a die. Okay, what is the time? Okay, 10 minutes. I will finish within 10 minutes. So in this, the average pressure required is P bar. Let's study the equation. Sigma dash f. What is sigma dash f? That is the flow stress corresponding to plane strain condition. How can we calculate? For example, for a material which already strained, our workpiece is already strained with the epsilon 1, then corresponding flow stress is sigma f. Here we consider unit width. So this is a plane strain, sorry, there is no change in the width. Width is not changed. So this is a plane strain condition. In plane strain condition, the von Mises stress criteria is that 2 by root 3 sigma f is equal to sigma dash f. So in plane strain condition, instead of sigma f, the amount of stress required for the deformation is not sigma f, this is sigma dash f. So that is this one, sigma dash f. So maybe in a problem, you may it may ask, the flow stress is equal to 5 megapascal. Then you have to convert this flow stress into 2 by root 3 in order to get this sigma dash f. If this is the problem is a plane strain problem, then only you need to convert into sigma dash f. If the problem is not a plane strain problem, we can directly convert this sigma, we can supply this sigma f here. Okay. The problem is a plane strain problem, only want to supply this sigma dash f. 1 plus mu a by h. mu A by H. Mu is the coefficient of friction. A by H. What is A by H? A is the length of the workpiece. Sorry, this is 2A. 2A is the length of the workpiece. Half of the length of the workpiece is A. H is the height. H is the height of the workpiece. So we can say this A by H is as an aspect ratio. This is called aspect ratio of the workpiece. Then my question, I have a workpiece 1 and another workpiece 2. Which one required higher pressure? Workpiece 1 or workpiece 2? This is 2A. Here this is 2A. This is H. This is H. Which one required higher pressure for the deformation? Workpiece 1 or workpiece 2?
Workpiece 2.
Workpiece 2, because workpiece 2 has higher A by H ratio. See this, A value is very higher compared to H. So the A by H ratio is very higher for this 2 workpiece compared to this workpiece 1. So with respect to A by H ratio and pressure are proportional. Then another question. This is my first forging operation. Without a lubrication between the die and workpiece. That is the first forging operation. Second forging operation, I supply some amount of lubrication in the interface. Which one required higher pressure? First case or second case? First case without lubrication, second case with the lubrication. Which one required higher pressure? Second case.
First case.
First case without lubrication. Second case with the lubrication. So when we use lubricants, the mu value can be reduced here. The mu value can be reduced when we use a lubricant. Okay. So when the mu value is reduced, of course this P value also will reduce. The pressure requirement for the deformation can be reduced. Okay. So that is the different important aspects from this formula. A by H ratio and this pressure is proportional, and this mu value also proportional. One more time is there, sigma dash F. That is also proportional to P. I am taking aluminum material with the same size and shape of steel material. Okay. Which one can easily forge aluminum or steel? Which one? Or copper. We can take copper or aluminum. Which one can be easily formed or forged? Compare the flow stress of the material. So when we compare, we can see the flow stress of the material in plane strain condition is very less compared to that of the steel. So we can say the aluminum material can need only low pressure for the deformation. So these are the three important terms used in the actually determine which affect the pressure requirement: the flow stress of the material, mu, and A by H ratio. Okay. So if we know the pressure value, just multiply the pressure, average pressure value we got here into area. This area equal to width into 2A. 2A into width. So average pressure into 2A into width, that is the amount of force required for the forging. So that is P average, that is this one. P average into 2A into width. We got the force. This is the second condition, that is slab condition. Then the question, what is the importance of flash? What is the importance of this flash area in the closed die forging? Here we can see the aspect ratio. In case of this bulk material, this is A, this is A, this is S. Okay. But in case of this flash, this is A, this is H. This is S. See the aspect ratio. A base ratio of the bulk material is very lower value, because almost same. A and H are almost same compared to the flash area. A base ratio. This S value is very small. So the A base ratio will be very large. So A base ratio of the flash is very higher than that of the A base ratio of the bulk material. And we already discussed the pressure requirement for the deformation or the force requirement for the deformation is proportional to A base ratio. So in the flash area, for the deformation, huge amount of force or pressure required, okay, than that of this bulk area. So that is the reason why the material will not flow through the flash region or parting line region instead of filling this area. The material will not flow. So after filling the entire cavity, then only the material flow through the flash area, okay, or parting line area. This is because of this high A base ratio in the flash area. This high A base ratio requires high pressure. So the flow of material requires high pressure in the flash area compared to bulk area, so that all the corner points will filled with the material. Then only the material starts to flow with the through the flash area. So that is the importance of flash, that is acting as a safety valve as well as it acting as a high pressure region which actually offer a resistance for the flow of material. This is because of the higher A base ratio. Okay, any doubt in this area? So initially we calculate the distribution, pressure distribution, which is a friction hill, but we don't know what is the constant pressure we need to apply through the die. For that, we calculate the average pressure. And using the average pressure, we calculate the force. This is actually the essential content of this lecture.